Given the continual surprising progress in AI,
powered by scaling up parameters and using more compute,
while using fairly generic architectures, e.g. GPT-3,
do you think the
current trend of scaling compute can lead to
human-level AGI?
And if not, what is the critical missing component?
Or do we need to do something fundamentally different? Hi, this is Jeff Hawkins. I'd like to congratulate Paul for the 100th episode of the Brain Inspired podcast.
This is Brain Inspired.
Yeah, so in fact, like you're the role model. Your podcast made me start a small podcast on my own that's called Stimulating Brains, because I really wanted to listen to a podcast about deep brain stimulation, which is my field, and there was none. At least I know none, and I thought that's a niche. And so even on the website it says that it's heavily inspired by your podcast, and the intro is similar because I just I try to learn from the best. Thank you so much for doing that.
Oh man, that is that's absurd and ridiculous. But thank you, Andy. It's also very kind. I'm glad you've been inspired to start your own podcast. So everyone, go check out Andy's Stimulating Brains podcast. It's at stimulatingbrains.org, where they discuss shocking topics. Oh, it's sad, really. I'm sorry. I couldn't help it there. All right, welcome to the third part of the 100th Brain-Inspired episode, Bonanza. I'm Paul, as always. Here is today's question that many of my previous guests answered. Given the continual surprising progress in AI, powered by scaling up parameters and using more compute, while using fairly generic architectures like GPT-3, do you think the current trend of scaling compute can lead to human-level AGI? If not, what's missing? All right, so there's the question for this episode. My terse response here is no. We cannot scale using what we have right now. Largely, that's because I, like a few other people who respond in this episode, reject the premise of the question. AGI, what is that? Human-level AGI, what is that? I reject the premise that that's a valid question. So I would have probably not responded to this question, but I appreciate the thoughtfulness with which many of my guests did here. So I ran all the responses through a recurrent convolutional neural network to determine the order this time. Not really. I randomly sorted the order in a spreadsheet, old school, lazy style. Like usual, in the show notes, I list each person and link to their information. So if you hear something you like, you can visit the show notes. braininspired.co/podcast/100-123. So we have a few more of these collections to go. And I want, again, to just thank all of the previous guests who took the time and made the effort to share their thoughts for this occasion. Please do consider supporting Brain Inspired on Patreon if you're getting value out of the show, which I hope you are. It's really quite cheap to do, and it's the sole source of income for the podcast. I don't do advertising. I hate advertising on podcasts. I understand it, but I hate it, so I don't do it. All right, away we go.
This is Wolfgang Maass from the Graz University of Technology in Austria. If scaling up is not sufficient, what's the critical missing component towards human-level AGI? A lot of thought and research at the moment starts to work on generalization, but this much more drastic form of generalization where you give test examples which doesn't come from the same distribution as the training example. And so they usually one refers to this as OOD generalization. And I think we know very little about the way how the brain achieves this OOD generalization. It's kind of an anecdotal insight there, but we don't really know how prior knowledge is really encoded in neural networks of the brain and how this prior knowledge is used to support abstract reasoning then. And this problem is related to the previous problem that I have sketched, namely take into account that the brain has been shaped by evolution. So therefore, I don't expect that we find there really a clean theory how the brain has managed to use prior knowledge to achieve OOD generalization. Then it may be a bunch of hacks which altogether work quite well then.
This is Paul Humphreys at the University of Virginia. I want to address the question of whether scaling up contemporary computational devices will enable us to reach artificial general intelligence. But I want to address this question from a slightly different perspective, in part by not looking at purely cognitive abilities, but emotional intelligence, and in particular the faculty of empathy, which is one of the ways in which human beings can bond with one another. Imagine that you are in a situation where your mother has just died, or your favorite pet has just died, and somebody, or an artificial device, is attempting to convey their sympathies to you. There's a major difference between a person who is pretending to be empathetic and someone who is genuinely feeling the suffering that you're undergoing. Now, there's little doubt that artificial devices will be, and in fact in some areas already have been, developed in order to behaviorally mimic the ways in which human beings interact with one another in these kinds of circumstances. But here the question is whether this would lead to a devaluation of human expectations about how to behave in those kinds of circumstances. We're all familiar with the ways in which people's modes of argumentation over social media have changed in the last couple of decades, and it has spilled over from the artificial domain into our interactions in real life. So suppose that we became habituated to artificial nurses in a hospital trying to console us after the death of our mother. We would not have the kind of expectations that we now do for real nurses, who in general are very highly skilled at conveying their sympathy with us in similar situations, perhaps because their own mother has died. So we become inured to a behavioral approach, which is very different from what our current expectations are. And then we would transfer this, perhaps, to our expectations from other human beings as well as from robots. Now, this may or may not be a good thing, but it will be different because we currently draw a sharp distinction between ordinary human beings and con artists, whether the con artists are swindling old people out of their life savings by pretending to be sympathetic with the elderly person's situation, or, in an extreme case, of serial killers. If there's no distinction between pretending to be empathetic with other people and actually having the genuine internal emotions, we will have moved into a different kind of moral territory than we now inhabit. And I'll leave it up to you to assess for yourselves whether you think that this is a good or a bad situation.
Chris Eliasmith.
I'm grouping these two together because I think they share an answer. Recall that the questions are, what is the most important disagreement in the field and what is the right direction? Do you think scaling with more parameters and generic architectures is going to lead to human-level intelligence? One important disagreement in the field is whether we need to worry about cognitive-level processing and representation or not. I think Gary Marcus and Jan LeCun had something of a Twitter war over this one, actually. Essentially, models like GPT-3 assume we don't. If we have enough data, we can learn everything we need to from that data, including what we might have thought of as conceptual organization, cognitive manipulation of concepts, how to usefully model the world, and all the relations in the world, and all this kind of stuff. So all that higher level cognitive stuff. At a more abstract level, you can actually think of this as a version of the question of whether we should allow ourselves to impose structure on the networks and representations in our models. This is a version of the same question because including concept-like representations is exactly an example of imposing structure on the network and representations. I'm actually a big believer in the importance of this approach for several reasons. One, it's resulted in huge successes in the past. Just look at convolutional neural networks. This is the workhorse of deep AI. Those networks adopt the structure we find in the biological visual system. Another reason is that nature has had billions of years to determine the right network structures and representations that we start with when we're born. So the amount of computation that evolution represents is kind of unfathomable. So we're going to have to jump the queue, if you will, in some way. And I'm guessing that the insights we get from neuroscience and psychology and good old ingenuity are the kinds of things that are going to let us not pay that huge computational cost. And finally, I come back again to the spawn model. There's really no way we could have started with a blank slate or a really deep generic network and just trained that network in order to give us a model that does what spawn does. Of course, because spawn is a neural network, we can actually backprop through the final version after we built it, and we can optimize. But to get it to that original functionality, using just backprop and a lot of data just isn't a viable option for several reasons. One is that models like GPT-3 cost about $12 million to train their 175 million parameters. If we assume that we can just scale by parameter count, spawn would still cost $1.4 million to train, and frankly, my lab doesn't have that kind of budget. Second, this approach assumes that there is a data set that covers the 12 different tasks that spawn can do. Unlike the terabytes of data on natural language, getting that kind of data for intelligence tests and copy drawing and so on just isn't possible. And third, we haven't seen much evidence that we can train a single model that does a lot of different tasks. Tasks like vision, motor control, reinforcement learning, intelligence tests, and so on. With this one big data set. This kind of heterogeneity of task is really foreign to most neural network models. So ultimately, I think that my arguments speak to a need for integrating methods. Not that one's better than the other. I love deep learning. My lab uses it all the time. But we also use concept-like representations, and we impose the structure of the mammalian brain on lots of our models. In some ways, the approach I'm suggesting here is what I argued for in my book, How to Build a Brain. It's an integrated hybrid approach to building systems that can achieve biological cognition.
Andrew Saxe here. Given the continual surprising progress in AI powered by scaling up parameters and using more compute, while using fairly generic architectures, do you think the current trend of scaling can lead to human-level AGI? I think the answer depends on how precisely you read the question. So that sometimes these questions can lead to apparent disagreement because people interpret them slightly differently. So if you take the question very literally, i.e., whether scaling compute can in principle lead to AGI, then I think you'd have to answer yes, because if you are allowed to train different subparts of the network in different ways, and you craft a very particular data set, then almost no matter what the end answer looks like, what sort of principles we end up embodying in a system that has AGI, you could probably train some network with some carefully set up tasks such that it would do a reasonable job of approximating that. But I don't think that's what most people mean, right? So the other interpretation is whether a standard deep network with today's architectures and learning rules and data sets that's just a billion times bigger is going to become conscious and clever. And there, I think the answer is no. Today's systems are taking really fantastic steps toward that goal. But they're only steps, and I think we have new concepts waiting to be found and discovered. What's the missing critical component, and how could we get these components fastest? Well, for starters, if I knew, I would be writing a paper right now, so I don't. But I think one important aspect is the richness of environmental feedback. So GPT-3 is trained on all of Wikipedia, but still it doesn't get the targeted instruction that humans get. And I think that dialogue with an intelligent agent who wants you, who's in a teacher-student relationship, where the teacher is itself endowed with incredible intelligence, all of our social learning abilities, these things give us, I think, a much better way of learning rather than the current approaches that rely on Wikipedia. And I also think part of the trouble is that we don't know what we don't know. So in terms of the practical ways, like how do you discover what you don't know most quickly? I think the answer is to strengthen our prospects for scientific discovery. And when it comes to neuroscience, we've developed a huge range of new methods that are exceptionally exciting, from neural pixel probes recording from thousands of neurons to calcium imaging and optogenetics. And my personal view is the epoch of methods development has already occurred to the extent that now we can go after the real scientific questions we're interested in. We can start to extract general principles. We can design experiments where animals are doing relatively complicated tasks. And the data coming back from those experiments, I'm sure, will surprise us and lead us towards what we don't know.
Mazviita Chirimuuta.
Yeah, the scaling up issue, it's like a betting issue. Like where would you predict things will go in the future? My bet is that you can't scale up to get human level AGI. I think expert systems, including the really powerful neural network architectures that you have today, like GPT-3, are really, really good and impressive at doing the things that they've been trained to do. And I think a lot of their power and effectiveness comes about because they're honing in on just particular functional or behavioral similarities that hold between the artificial system and the brain. But to get to human level AGI, there's going to have to be a whole lot more going on that is just not captured by a system which just relates to or corresponds to a biological brain in just some narrow respect. So that's my reason for thinking that just making bigger and bigger technologies of the same sort that we have today will not lead to AGI.
So the critical missing components would be like all the biology?
All the biology, but I think some of the biology, I mean, like the context that the brain has as one organ in a body, plus that it's made of metabolizing tissue. I think that's going to be part of the story about how biological intelligence is general, and those are just not part of the technology that is there today.
This is Steve Potter from the Georgia Tech Laboratory for Neuroengineering. Okay, so we're talking about components for general AI and, human level AI. I would say that AI experts are obsessed with using some technology that's completely incongruent, which is digital computation, to emulate a completely analog thing, the brain. Yes, perhaps by using a large warehouse full of servers and an entire hydroelectric power plant, we may eventually see human-level AGI on a digital platform. That, compared to a living brain that uses less than 100 watts, will be an embarrassing accomplishment. We ought to be trying to model and emulate the brain using a substrate that is more like it. In other words, analog, not digital.
Blake Richards. No, scaling up by itself is probably not going to provide the entirety of the answer. However, I will add the following caveat. We've seen a remarkable amount of progress simply by scaling up. Furthermore, there are two ways in which there's still a lot of space to scale up to what brains actually do. The first is just the size of the networks. Everyone knows that the networks are getting bigger and bigger, but they're still not at the same scale as real brains. So we still have a ways to go before we can say that scaling up to the size of real brains wouldn't necessarily give us additional advantages. The other, and in my opinion, even more important question of scaling up is the question of scaling up the data sets. And by this, I don't mean the amount of labeled data or something like that. What I mean is literally the richness of the data. If we consider something like GPT-3, it's just been raised on a corpus of text. That is the entirety of its experience of the world. In contrast, human beings are raised in this incredible multimodal world where they can act and they get things from 5 different senses, and there's a coherence to everything and rules of physics that apply to all of the interactions, etc. And then they learn a language on top of this experience. So my personal guess is that we can also achieve a lot simply by giving our AI more naturalistic experiences of real, rich, multimodal worlds where they can act in them. And this is actually a really hard problem for scaling up because honestly, to properly simulate the kind of experiences that, say, a human baby has would be an immense amount of computational resources. So there's a lot of scaling up we can still do. Now, as I said at the beginning, though, do I think that'll take us all of the way there? No, likely not. And I think the reason is that we have seen time and time again in AI that picking the right inductive biases is incredibly helpful for solving a problem. And my guess is that the inductive biases that exist in, as you put it, fairly generic architectures like GPT-3 are not suitable for inducing the sort of understandings of the world and representations that the human brain likely has. Basically, I suspect we have additional inductive biases that are missing from these systems. And I suspect those inductive biases will be key to getting the scaling up to give us something more like human intelligence. But I think the scaling up is also probably critical and will buy us a surprising amount.
This is Paul Cisek from the University of Montreal. So I think no, I absolutely don't think that scaling up just by adding more computational power is going to get us to human level AI. And I think for the most part, really, we're still just solving the same kinds of problems that we've already been solving for a long time, essentially mapping problems between, again, input and output, an image and a labeled model. And I think the kinds of problems where we've succeeded are ones where success is defined as meeting the criteria of some external supervisor, like a programmer. And I don't think scaling that up was actually going to go beyond. If we scale up our performance on other mapping problems, that's great, but I don't think it's going to lead to human-like AI, because that would actually have to be its own supervisor. And I'm not talking about unsupervised learning. Of course, there's many systems for doing unsupervised learning. What I mean is we have to build systems that discover and define their own criteria for what success in the task is. And I think that is not being done, and that won't be suddenly achieved if you just scale up. Although I do think that research on reinforcement learning is quite promising, because I think that is probably the path toward systems that do discover and define what success is. But I think the missing component, when you ask about the missing component, I think it's the same one that's always been missing, and that's the question of meaning. So good old-fashioned AI systems failed to achieve human-like AI because they were really just about syntactic rules for manipulating symbols, etc., without any regard for the semantics that those symbols are supposed to capture. And then neural networks replaced symbols with vectors and if-then rules with matrices, but the tasks that they solve are still essentially syntactic and not semantic. So they don't capture meaning. And many people have been saying this for decades. You know, John Searle said this in the 80s, Stephen Harnad in the 90s. Now Melanie Mitchell and many others are saying the same thing. And as far as I can tell, everyone who has actually thought about this issue pretty much agrees that this is a central issue that we need to address, and that current approaches, just scaling up current approaches, doesn't really address it. But I think the problem is a lot of people are just not thinking about these issues because they're kind of philosophical issues. And maybe, they feel like their time is better spent to just, try to build the next system that impresses us with its, superhuman performance in some new mapping task. I think recent advances have made a lot of people think that we're making such great progress that the big insights are just around the corner, and we just need, and we're like all in a race to get there as fast as we can. But I don't think that's the case. I think we're rushing, smashing ourselves into the mountain as fast as we can instead of, trying to hike up around it, sort of find the path around it that's more slow. I think a lot of people, by ignoring the deep philosophical gaps which I think most people acknowledge that consider them, and including many of the people that work in AI, they acknowledge them. But I think apart from that, there's just so much excitement that people rush into the field with that they think, well, I'm going to make the next bigger system and that will be intelligent. I don't think that's the case. Of course, I could be wrong.
This is Brad Love from UCL. All right, next question. Given the continual surprising progress in AI powered by scaling up parameters and using more compute, while using fairly generic architectures, e.g. GPT-3, do you think the current trend of scaling compute can lead to human-level AGI? I don't think just more of the same is going to, give you AGI. For example, when you train more and more on the same type of data or just make the same kind of architecture bigger and bigger, diminishing returns are going to kick in. And if you take GPT-3 as an example, it's amazing, but what it's really doing is just passively observing a lot of text. And it's building really interesting embedding spaces. And I think it's showing systematic understandings of domains. I'd like to test it more, but, it's not a reasoning system. It's not even really about language understanding. It's a language model, and it's a quite good one, at least from my perspective, from an information theory perspective, because what I would want my language model to do is reduce my uncertainty in, which word is going to come next. And GPT-3 is great at that. So I guess, what are we going to need to actually get to the human level AGI? I think one problem with things like GPT-3 is it's really just learning in one modality, right? It's just observing text. And of course, first, there's this issue too of, you need to be actively engaged with your environment. So you think of a child just playing and, bouncing a ball around or banging it on their head. Not only are they actively engaging in a complex environment, but they're getting multimodal information, so just not a bunch of words coming, right? They have visual feedback. They have, feedback from their arms or muscles, propriosensory feedback. And so I think when we have all these different kinds of embedding spaces we could build for the same event, and we could link them together, then we can get a richer understanding of a domain. So like Brett Rhodes and I have a paper in Nature Machine Intelligence on this, and I think this is really true. So we can't really just make these systems that just do one thing, one modality, just words or just images. But they have to link these embedding spaces. And, people do that, but I think that's a really promising direction.
I'm Jay McClelland. I think that, of course, that general artificial intelligence is going to continue to benefit from scaling up, and that in some ways we have just a huge further distance to go in terms of reaching the kind of scale that, the parallel distributed processing systems we have in our brain offers us. At the same time, I don't really think that the kinds of agent models that are currently exhibiting, surprising successes are going to eventually solve the problem. And, if you read the GPT-3 paper, the authors seem to share that view. they appreciate many of the limitations that their model has, and they expressed considerable hope and expectation that they continue to be able to make improvements, but not just by scaling it up. There were several interesting ideas in their paper about directions to go. Speaking for myself, the way I've thought about this is, what would it take to create an artificial PhD student? Somebody who could attend classes, take notes, think about the ideas that other people have offered, start developing their own ideas about what they wanted to pursue for their research, and, draw on the ideas of others and build a program and a direction for themselves, and end up being somebody like, Jeff Hinton or Dave Rumelhart or even Einstein and Isaac Newton, right? These are all people who came into a field, saw where things were, saw things that weren't kind of problems that weren't being solved, spent a lot of time thinking hard about how to solve them and developing new ideas. And I think that really requires, developing more agency in our agents, right? The agents we have now are reacting to environments. Maybe they're engaged in certain kind of rollout-like behaviors that start to look like planning and thought in ways that are certainly interesting, but they don't have any sense, as far as I can tell, of a long-term ability to formulate a goal and to work towards a goal. And I think that as a general matter, AI isn't really quite as goal-directed as it should be. Even, reward maximization isn't the same as, wanting to get gas in your car. I mean, wanting to get gas in your car is a very specific thing. Which gas station is open, right? If there's gas shortages, where are there lines and stuff like that? So you're planning very much in a very specific problem space about a very specific goal. And we need more of that, and we need more of agents that can have these goals over very extended time periods, and the way we do when we're planning a research agenda or something like that.
Let's take a quick little break, and then we'll get back to the responses.
My name is Asya Mofrad, and I'm finishing my PhD, hopefully soon, in Norway, Oslo University. During my PhD, I was searching for how these computational models used for psychology, and then I discovered James McClelland. I mean, I haven't thought that he's a well-known person, so I was searching for him to get familiar with the talks, and then I listened to your very inspired interview with him. But the way he answered your questions, and he kind of positive, and he was really instructive. The kind of question you had with him at the end was kind of made me courage to email him and see if I can visit him. I mean, I'm not sure if I email other guests of you, maybe they will respond me this way, but he was really nice. Some kind of discussions, general, like academia versus industry, these kind of questions was also useful for me, because I rethink about should I stay in academia or should I go for industry. And at some point, because I see there are many people who are doing really great jobs, and think, okay, you don't need to stay in academia, you can go on do something else, because there are many great scientists who are really doing better jobs than you. So,
Megan Peters, University of California, Irvine. Given the continual surprising progress in AI, powered by scaling up parameters and using more compute while using fairly generic architectures like GPT-3, do you think the current trend of scaling compute can lead to human-level AGI? And if not, what is the critical missing component? So my answer is no. I don't think that more and more compute is going to solve the problem. I don't think that it's going to magically create a breakthrough to just crank up how much horsepower we throw at a particular problem. I feel pretty strongly, actually, that there are some components to the system that we don't really understand yet and that we don't understand how to build yet. Gary Marcus actually talks about the need for what he calls a substrate to support the capacities that are necessary for AGI, artificial general intelligence, to be able to flourish. And not about just building an AI with certain capacities in a modular kind of way, but building this substrate to support those capacities in their development. So we can't just take like the compositionality module and the symbolic manipulation module and the meta learning module and like plug them in to make a super AI. So I agree with him that that approach isn't going to help us build an AI that can actually be truly intelligent, could actually learn how to maximally or optimally use these types of capacities that we might give it in this modular sense. And certainly that kind of modular approach is not going to allow an artificial intelligence agent to work on developing these certain capacities beyond their original programming, which I kind of think is one of the things that drives our own intelligence, the capacity to kind of evolve to fluidly switch between these modules to decide when each module is appropriate and how to best use it in that instance. So I think I'm going to copy Gary here, at least in a small way, and at least insofar as saying that we need something like what he calls this substrate. We need to develop an infrastructure that can support an agent in selecting these modules like we would, or even in developing new modules. And I think that that's something that we probably can't get from just throwing more and more and more compute at the problem with our existing toolkits.
Hi, Paul. This is Dean Buonomano. Given the continual surprising progress in AI, powered by scaling up parameters and using more compute, while using fairly generic architectures such as GPT, do I think the current trend of scaling compute can lead to human-level AGI? So GPT-3 is indeed spookily impressive, and in many ways it seems to have essentially passed the Turing test. But ultimately, I think it's really an example of the amazing power, the astonishing power of statistically guided mixing and matching of words and sentences. So in some ways, I find AlphaZero Chess and AlphaZero Go more impressive because they've clearly exceeded human performance, where GPT-3 is basically using human templates that it was exposed to mix and match words and sentences. What I was particularly surprised about with GPT-3, at least as I understand it, is that there's no recurrency. That is, its neural net is entirely feed-forward. This is, of course, in sharp contrast with the absurdly recurrent nature of the brain circuits, which is the brain is littered with positive and negative feedback. And I expect recurrency and feedback is critical for AGI or artificial general intelligence. For example, it's hard for me to imagine how the GPT architecture would support coming up with two hypotheses and mulling them over and then reporting which one it thinks is best. I don't think the GPT architecture supports that. So I don't think that type of architecture will scale up to AGI. Additionally, it should be said that your question is a bit of a trick question because nobody really agrees to any fixed criteria or fixed definition of what AGI is. Perhaps we'll know it when we see it, or perhaps enough knowledge and statistics will pass as AGI. I don't know. But if we go back to the 50s and 60s, many people thought that beating a human at chess should be taken as proof of human-level reasoning and intelligence. But we changed that bar pretty quickly in the 90s for obvious reasons. So similarly, I think AGI will be a moving bar for a while.
Talia Konkle.
Given the continual surprising progress in AI powered by scaling up parameters and using more compute while using fairly generic architectures, for example, GPT-3? Do you think the current trend of scaling compute can lead to human-level AGI? I guess I reject the premise. I'm like, I don't know what human-level AGI is. I think I may be a bit contrarian on this one. I think we're good at a lot of different tasks, but also because we practice a lot of those tasks. And I don't quite know what human-level AGI is, so I can't answer that question.
I'm Steve Grossberg. Given the continual surprising progress in AI powered by scaling of parameters and using more compute, do you think the current trend of scaling compute can lead to human-level artificial general intelligence? Well, my previous reply leads me to say no, if you're going to use deep learning, but yes, if you use neural architectures such as the predictive art architecture that I published in 2018, and you can download from my webpage, sites, sites.bu.edu/STEVEG, sites.bu.edu Steve G. This predictive art or part architecture includes multiple parts of the brain, each carrying out functions that are enabled by their interactions with other brain regions. Moreover, new and really revolutionary computational paradigms underlie our brain's astonishing abilities to adapt to changing environmental challenges. Two of the paradigms that I was lucky enough to introduce are called complementary computing, which clarifies what is the nature of brain specialization. Why are there so many brain regions doing parallel processing with multiple processing stages? And laminar computing, which asks why are all neocortical circuits organized into characteristic layers?
I'm Nathaniel Daw at Princeton University. I think it won't by itself. I think it's, I've been around long enough to see the pendulum swing a few times, and I think it's obvious that it's going to swing back towards more understanding, more theory, and not just sort of this engineering approach of like dumping more and more data in larger and larger models and sort of tweaking things and seeing if you can get it to work. Like that's worked surprisingly well, and that's great. But the last phase of this ended with a lot of stuff that was more motivated by theory and kind of higher level understanding, and that works too. And I think the most exciting stuff in AI already right now is stuff that's a little more nuanced and involves a sort of mixture of sort of classic algebraic methods that do the parts that are statistical methods that do the sort of parts that are amenable to that, augmented by deep networks for other parts that are amenable to the things they're good for. So things like the sort of line of AlphaGo algorithms and networks, they sort of integrate regular old research with sort of deep networks in sort of clever ways. And I think that's where the future is.
Okay, so my name is Marcel van Gerven. I'm chair of the AI department at the Donders Institute. Yes, but there are some problems we need to fix first. So scaling up, yes, that's very nice, but we also live on a planet with finite resources. So if we do the scaling up, we definitely need to make things more efficient, right? So I think that will be a big undertaking, and that's also what you see happening. People moving away from using large GPU clusters to doing computing on the edge or embedded systems. Working on TinyML solutions. So really trying to think about, okay, how do we do this in a much more efficient manner? And then working on TinyML, that's one way to do it. working on neuromorphic computing solutions, which really embrace event-driven computation. That's another solution, but I think in the end it's also about bringing computation closer to physics. So there's also quite a bit of work in material science that is trying to make materials ready for computation. So really trying to do things at a more atomic scale, and that will definitely help us improve the efficiency of current AI systems.
Kanaka Rajan. Before I get into the answer, right, these advances, GPT, for instance, are astounding at what they're trained to do. So let me state that up front. Just the claim that they're going to do all of the things magically bugs me, because it sounds almost like a religious stance. So that said, do I think that the current trend of scaling compute, without changing anything about fundamentally the architectures or anything, can lead to human level AGI? Plainly speaking, no. Scaling compute is basically the same as algorithmically, as filling a giant lookup table, brute force. So, someone recently quipped that it was like trying to go to the moon by building a tall ladder. So, I may have somewhat heretic views on this compared to the traditional ML bro you talk to. But first, yes, humans, we do a lot of things, some at the same time even, but none of them perfectly well. So computers, even calculators, have been outperforming us for decades now. So there's that. But the key is that they do so in specific things. The second thing I take issue with is the exceptionalism implied by such a goal statement. That is, that human brains are somewhat this mystical, magical pinnacle of generalized intelligence. Yes, we're smart. Yes, we have Bach and math and music, but other nervous systems, including not even strictly embodied ones like cephalopods, do a number of pretty amazing things behaviorally. And, all of the biology that got there through evolution and through very different wetware. So let's at least pretend to care about these aspects of biology. I mean, it is brain inspired. So what is the critical component, right? So that's the second part of this question. And what are practical ways to obtain such components? I think understanding, that's one. So does GPT truly understand what it's generating responses to? Compositionality is another aspect that comes to mind. So even, I hesitate to even use the word proto-languages, but something like whale song, right, contains elements of compositionality. So I think that the fundamentally noteworthy theoretical advances towards understanding cognition, and then eventually emulating that in, human level AGI systems, will come from novel network models that incorporate more biological architectures like, feedback, recurrent connections, multi-region interactions, complex neuron-like units, time-varying patterns of activity dynamics, and then partly or fully unsupervised learning algorithms. So practically, I say talk to neuroscientists, or generally scientists whose models are geared towards being able to understand how biological wetware implements the functionality one is interested in.
This is John Krakauer. No. I think, it's interesting. Take, for example, you mentioned GPT-3, right? So there are people who will say that if you look at the paper, unusual things begin to happen at some scale. Like suddenly it can add numbers when in fact it was never given, addition to learn overtly. So there are emergent properties that seem to come along just by scaling up, as you were. But no, I mean, it does sentence completion. That's what GPT-3 does. It doesn't understand things. And the idea that suddenly just doing more of the same, understanding will suddenly just pop out, I feel is a very, very odd stance to take. I don't think it's clear how to proceed. There are some people in AI who believe that you have to come up with some more circumscribed definition of thinking. And one idea might be that thinking is the ability to fill in the incomplete knowledge that is right in front of you, in other words, the world in front of you, with knowledge that you bring from your past, and somehow you can use that knowledge to dictate your behavior at that moment. And thinking is this ability to bring knowledge to bear on your current context. Now, whether there's going to be an ability to formalize that and to define it in such a way that you can get traction on it is unclear to me. I think there are people in the world in AI who know this and realize it's a problem. How do you bring declarative, overt knowledge and facts to bear on decision making, and do it in a way that you're not just going back through the back door to GoFi and programming it all in? But, people like Gary Marcus, I think, will say, just accept that you're going to have to do both. Find a way to program in knowledge and then have that used in some way by deep neural nets in combination. But it's a complete crapshoot right now.
So I'm Rodrigo Quiroga, neuroscientist at the University of Leicester. I think we're still not looking deep enough to how the human brain actually works. And this is my research. I record the human brain and I see some principles which are kind of like on the antipodas of what we see in AI. And if I keep it at a very simple level, in principle, a computer will just replicate information but the computer does not have understanding. And I think a basic principle of how the human brain works, and particularly for memory, which is what I study, is that we forget a lot. There's a lot of information that we don't even process. So we're very good at extracting very little information that we consider to be meaningful, extract some sense from this information, and then working with this sense that we extract from that. So this process of abstraction, of going to the higher level thinking, if you like, involves a lot of forgetting, because in order to abstract something, you have to forget details. You have to leave details aside. And of course, this leads to a lot of errors, no? Because the moment you forget details, there are things that, you will miss. And I think the way we have been developing computers in general, machines, is not to have these errors and therefore not to forget things. But I think this is the opposite to what you want to try to see if you can somehow replicate human level intelligence, which is based on forgetting a lot of information and developing common sense in order to do the things that I'd said before: general intelligence, ability of abstraction, making inferences, and so on.
Grace Lindsay. I am a postdoc at the Gatsby Computational Neuroscience Unit at University College London. Do you think the current trend of scaling compute can lead to human-level AGI? I'm going to include scaling data in this as well, because GPT-3 uses a lot of data as well. Probably not. No, I don't think so. Especially if you want to mimic human learning, maybe you can get an artificial agent that's very good at a task by giving it, 8,000 human years worth of time to learn and all of the written, language in the world or something like that. That's not what humans have. That's not what they use to get to human level intelligence. So certainly if you want to replicate the learning of humans, I don't think that just more compute and more data is going to be the answer. Also, I guess there's probably something to the versatility of humans and the fact that it's, a single brain doing so many vastly different tasks, from motor control to sensory processing to planning and all those kinds of things. And I don't even know what more data would mean in that circumstance. You'd have to have kind of all data about everything. So yeah, I don't think just pure scaling is going to be the ticket to human level AGI. I think it'll get you far on certain specific tasks. like a single agent doing a single task. You can probably get pretty far just by scaling with compute and data. But an integrated agent that learns at the rate of humans probably needs something else in terms of advances in learning algorithms or architectural modules. Honestly, I have no idea, because if I knew, I would publish it.
My name is Konrad Kording. I'm a neuroscientist at the University of Pennsylvania. Given the continual surprising progress in AI powered by scaling up parameters and using more compute, while using fairly generic architectures, e.g. GPT-3, do you think the current trend of scaling compute can lead to human-level AGI? I absolutely don't think that. So if we look at GPT-3, it's in a way a really big lookup table, not like it's been trained with everything that humans have ever said, or at least a significant subsection of that. So in that sense, the answer to most questions is already in that data set. But a lookup table isn't intelligence. The thing that makes us be so impressive in a way at solving difficult tasks is that we can deal with new situations based on very, very limited amount of data. GPT-3 cannot do that. And it's not that there's something wrong about GPT-3. It is just that GPT-3 completely lacks what makes human intelligence so interesting. It cannot argue internally. It cannot tell stories. And in fact, the thing that makes texts written by GPT-3 so sad is that it completely gets story wrong. So if the question is, what are the critical missing components? I think, if you ask me, the critical missing component is the ability to tell stories. Let me highlight why I think this is so important. The world around us, the world that we construct with our friends and families, is very much a world of stories, where we talk about high-level phenomena, and we, over very short periods of time, maybe a few minutes, go through something that might otherwise take a really long period of time. And I think one of the things that we're critically missing is machine learning systems that really tell themselves stories.
This is Jeff Hawkins. Can we get to human-level AI by scaling our current systems, or do we need to do something fundamentally different? As long as I've been interested in the field of intelligence, I have believed that we first have to study the brain. We have to study the brain to not only learn what mechanisms are used in the brain to create intelligence, but to learn what intelligence itself is. For I don't believe we have a good working definition of intelligence. Today's AI is focused primarily on solving particular tasks, using particular techniques that seem to work, but without a fundamental understanding of what intelligence is. Here's what we've learned by studying the brain. We've learned that intelligence is based on the ability of our brain to learn a model of the world. We have a tremendous amount of knowledge about the world in our heads, and it's stored in a model. The model tells us what things look like, what they feel like, what they sound like. The model tells us where things are relative to each other, and the model tells us how things change as we manipulate them and as we move about the world. It is the model that is the basis of intelligence. Not any specific task that we might accomplish, but a model allows us to accomplish almost any task. We can ask, given our model of the world, how we might achieve a certain result, or what will happen if we take certain actions. We've learned a lot about how the brain learns a model of the world. I'm going to just talk about 3 high-level components. The first is we learn through movement. When we learn a model of the world, we don't just sit statically and look at images. We move our bodies. We move our eyes constantly. We move our fingers. We pick things up. We poke things. We touch something and see what it sounds like, see what it feels like. We push things. We try things out. We have to move through the world. We have to move our senses to the world. We have to interact with the world to learn. This is almost completely lacking from today's AI. The second component of how the brain learns a model of the world is how it stores information. How does it store knowledge? What we've learned is that the brain stores knowledge using reference frames. You can think of a reference frame like our Cartesian coordinates x, y, and z. It's a structure that is a metric structure, meaning the brain assigns knowledge to it. So when it wants to learn something, it assigns the sensory inputs to locations in a reference frame. In the brain, these are implemented by types of cells called grid cells and place cells. And we've figured out that grid cells and place cells exist throughout the entire neocortex, which is the organ of intelligence. It's essential to have a way of representing knowledge. And reference frames are the way that brains do this. Today's AI do not have anything equivalent to this. And finally, the third big topic I want to talk about, what we've learned about brains, is knowledge in the brain is distributed in a certain way. If I ask you, where is knowledge about a cell phone in your brain? It is not in one location. It is not in two locations. It turns out that in your brain, specifically the neocortex, you have thousands of models of your cell phone. They are complementary models. There's models of what your cell phone looks like. There are models of what your cell phone feels like. There are models of the sounds it makes. And so knowledge is distributed across many, many models. In the human neocortex, there's about 150,000 cortical columns. Each one is a modeling system. So it's a highly distributed system. And I believe that you have to build intelligent systems this way too. It allows the flexibility of integrating different modalities, such as hearing, touch, and vision. It allows the system to deal with ambiguity, because some models will be understanding some parts of the world, and others will be understanding other parts of the world. And allows us to build intelligent machines in different embodiments that can have all types of different shapes. They don't have to look like humans. So again, the three things I'm arguing that are missing in today's AI, three huge things, are learning through movement, storing knowledge in reference frames, and a highly distributed modeling system. We've written a series of neuroscience papers about this, and we call the overall theory the 1,000 brains theory. And we've just started taking these ideas and implementing them in machine learning and AI. We think that is the future. I've also written a book that's coming out in March called 1,000 Brains, which will cover this topic, both from a neuroscience and an AI point of view. Thank you for listening.
Uri Hassan from Princeton University. So I think that the scaling in AI is minuscule relative to the brain. You know, GPT-3 have 150 billion parameters. That sounds like crazy. If I'm taking 2 voxels in the brain, 6 millimeters of cortex, I have more synapses than GPT-3. So the scaling in the brain is way larger than what we see in machine learning. So I'm never scared about this scaling argument. Saying that, I think that the foundations of the brain and the foundation in machine learning are very similar. The brain is also using a direct fit and blind supervision in a closed loop dynamical system approach to fit to the world without understanding. So I see deep connections between the brain and this machine learning. But this is only the starting point. It will be a mistake to say that machine learning have any intelligence, but humans do. So while I think that the foundations are very similar between human and machine, something is really missing in machine that we have in humans, right? We can understand physics, we can understand rules, we can have calculus, we can go to the moon, we can think. These machines do not think. So I think that while the foundation is similar, the next stage in AI and in cognitive neuroscience is to understand how from this blind fit and overparameterization and memorization and interpolation and fitting, you can go to the next stage of extract information about the world by taking the shape of the world. So that's something that we will need to think about. And it's really missing in machine learning currently.
My name is Jessica Hamrick. Do I think the current trend of scaling compute can lead to human-level AGI? No. I think that while, of course, the recent advances are very impressive in terms of showing what we can do as we do continue to scale up compute and data, I think having a generally intelligent system requires both lots of experience and being able to choose the experience that it performs on the world. So you need systems that are able to perform interventions on the world and learn from those interventions. I think just treating the problem as a supervised learning or prediction problem isn't going to get us there. But then when it comes to actually scaling up the compute and data for actually performing interventions, I think that this is really hard and not something that is easy to do. We can train, for example, agents in simulation, which of course can learn to interact with the world. But these simulations that we can develop are really impoverished compared to the real world, especially if you compare to like the, millions of years of evolution and the vast complexity of the natural world. There's so many different species, so much complexity in the real world that we've evolved to learn to interact with. And that's not something that we are currently able to replicate in simulation at all. And of course, we also don't want agents sort of just running wild in the real world. And so there's a real question of how is it going to be possible at all to really scale up the data and compute to train these types of agents? And I think the answer is probably no. And for that reason, I think that we need to adopt a hybrid approach where we look for like what are the most promising types of inductive biases or structures that we can build into agents that we know evolution like settled on as good solutions to the problem, figure out how to combine those with powerful learning systems so that we don't have to replicate the entirety of evolution. Because I think that that's basically what we were saying is what we would want to do is like with enough data and compute, we can replicate evolution. But I just don't think that is really a possibility.
Thomas Naselaris, Department of Neuroscience, University of Minnesota. Do you think the current trend of scaling compute can lead to human-level AGI? No, I don't. Why? And what's missing? It's something like creativity, which I think requires very efficient world modeling that would lend itself to testing hypotheses about causality and the consequences of one's and other agents' actions. I would guess that emotion is also an important part of AGI. I'm just guessing. I know very little about that. But it's certainly salient, and it certainly guides a lot of the way that we think. And I'm not at all convinced that it's something that we can be smart without. Emotion, that is. What are the practical ways to obtain such components fastest? More funding for basic neuroscience.
Brain Inspired is a production of me and you. I don't do advertisements. You can support the show through Patreon for a trifling amount and get access to the full versions of all the episodes, plus bonus episodes that focus more on the cultural side but still have science. Go to braininspired.co and find the red Patreon button there. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thank you for your support. See you next time.
The